Section 9.2. The chemical potential of a component in the gas and the solution phases. Let's talk about solution. Let's say we have species I in a solution and its vapor in the gas phase. Assuming the solution and the vapor are at equilibrium, then we can say the chemical potential of this species I in the solution is the same as the chemical potential of the vapor of species I. So we write out this equation. Mu is the chemical potential. We're talking about species I in the solution versus in the vapor. And we learned this equation before for ideal gas. The chemical potential of a gas is equal to this chemical potential of 1 bar pressure plus a correction. The correction is just RT times the logarithm of the actual partial pressure of that species divided by P naught. In this case, for a pure I, 100% I, in the liquid phase, we have this notation, mu sub I, and this asterisk denotes pure. So the chemical potential of pure I now is equal to, well, we have a similar equation here, similar to this, except that we put an asterisk in the superscript here to emphasize this is the vapor pressure of pure I. Now we have two similar equations. One is this, the other one is this I in the solution. We take the difference, so we have mu of I in a solution minus mu of pure I right here is equal to this two terms minus this two terms. The baseline over here, this is the chemical potential of vapor I of 1 bar pressure. They cancel. Then we combine this two. It's going to be just RT times the logarithm. The baseline P naught and P naught cancel. So it's going to be just Pi over Pi star. Now this equation is pretty simple. The difference between this chemical I in a solution and this chemical potential of pure I is simply RT times the logarithm of the ratio of their vapor pressures. Raoult's law states that the chemical vapor pressure of component I is equal to its mole fraction in the solution times the chemical vapor pressure of pure I. So we plug this in here. Pi star and Pi star cancel, and over here this becomes Xi. Therefore, the chemical potential of I in a solution is the chemical potential of pure I plus RT times the logarithm of the mole fraction of I. And then we can look at the change of the Gibbs energy of this component I before and after mixing. So it's denoted by delta GI mixing, species I. And this is a mixing process. We're looking at the change of Gibbs energy. This mu is corresponding to the molar Gibbs energy, so we need to multiply the difference. This is before mixing, this is after mixing. We need to multiply this by the number of moles. Therefore, we have Ni times this part. It's going to be NiRT times L1Xi. And this N sub I is the number of moles of I. This is actually N times Xi, and is the total number of moles of all components in the solution, and X sub I is the mole fraction. The reason we do this is because if we have two or more liquids being mixed, the total Gibbs energy change is simply nRT times the sum. The sum of what? The sum of this. So this is for species I, and then we can sum this over from the first component to the last component. If you look at this equation and compare this with the Gibbs energy of mixing for ideal gases, you will see they are exactly the same. No difference at all. Again, this is Gibbs energy of mixing, and is the total number of moles of all components. R is the ideal constant, T is the temperature. Let's assume we are mixing those components at the same temperature, and there's no temperature change. Why? Again, in this case, we're talking about ideal solutions. All right, in an ideal solution, yes, molecules do interact with each other because they are close to each other, but the change of the interaction is zero. Remember, for an ideal solution of two components A and B, the AB interaction is the same as the AA interaction. And also it's the same as the BB interaction. So when you add A into B, it does not change the interaction. Every B fails. And same for A. Alright, okay, here's the sum of xi times Lxi. Again, this equation can be used for the mixing of ideal gases. And also here, it can be used for ideal solutions. And then we can easily compute the entropy change. It's simply delta. Oh, well, this is lowercase delta. This is the uppercase delta G mixing. This equation comes from the definition of G, actually. G equals H minus Ts. H is U plus PV. And eventually you'll get this dG equals negative SDT plus VdP. Alright, so in this case we learned this entropy is simply dG over dt. It's negative dG over dt. Okay, it's negative dG over dt. So delta S is negative d delta G over dt. So that's what you're looking at here. When you look at this and you realize over here, this delta G mixing does include temperature in the formula. Therefore, this entropy of mixing is simply the first derivative of this with respect to temperature. And don't forget this negative sign. So you put a negative sign in front. When you see this negative sign, don't rush to a conclusion that this is negative. It's impossible. After you mix two components, the entropy change should be positive. Why is this positive? Very simple. X sub I is always less than 1. So this part is always negative. Therefore, this product is always negative. The sum of negative numbers is negative. And then this negative sign tells us the entropy change in a mixing process is positive. Well, how do we get the volume change after mixing? For an ideal solution, this volume change is 0. Alright? You may want to say if we mix water and ethanol, the volume actually shrinks. Well, it's true because this solution, this water ethanol solution is not an ideal solution. Right? And actually there's no ideal solution in this real world. So this is just providing a starting point for us to understand the mixing of solutions, the mixing of liquids to form solutions. Alright, so dG equals negative SDT plus VdP. So volume is just volume V is simply dG over dP. So delta V is simply d delta G over dP. So it's 0. How do we get this enthalpy? Enthalpy is just G minus Ts. It's 0. Internal energy is H minus PV. It's also 0. So during the mixing, the volume is constant. We're doing the mixing under constant pressure condition. So neither P nor V changes. And also, we don't need an equation for this. Just remember, the interaction between AB is the same as the interaction between AA, and it's the same as the interaction between BB. So when you add A into B, indeed you changed the environment of B, but still the change of interaction is 0. And when I say interaction, it means attraction and repulsion between those liquid molecules. Alright, so if you look at these equations, delta G, delta S, delta V, delta H, delta U, they are just exactly the same as those for the mixing of ideal gases. I didn't put delta A here, but you can prove this delta A mixing is the same as delta G mixing. Okay, delta A mixing is the same as delta G mixing. Why? A is G minus PV. And over here, we just mentioned the pressure remains unchanged. The volume remains unchanged, therefore the change of the product of PV is 0.